Hello guys, welcome back. Now for the higher levels, we're going to be doing a couple things today. First, let's go over a derivation of the equilibrium expression from kinetics. We know that, so let's go to our whiteboard here. We know that at equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. Now let's consider one elementary reaction here. Let's consider the reaction between HA. No, let's actually generalize this a bit more. Let's generalize this. A is equal to B plus C. Let's generalize that a bit. So we know that the rate of reaction is equal, the rate of this reaction is equal to, and since we know that this is elementary, we know that rate equals K times A. Now, similarly, since this is elementary, the reverse reaction should also be elementary, and we know that rate forward is equal to that, and you know that reverse rate, 8B, is equal to K times B times C. Now, we know that at equilibrium, let's rearrange for K, so implies that K equals rate forward over the concentration of A, and this implies that K equals rate backwards over B and over C. Now, since we want the forward rate on top, we're going to divide through. We're going to divide this by this, so F over KR, FR, so K, let's actually do KR over KF equals 8B over the concentration of B times the concentration of C over rate forward over the concentration of A. Now we know at equilibrium that these two the backwards rate and the forwards rate are equal to each other. So, and since we know that's how math works, but alternatively, let's divide through. So 8B over B times C. Oh, I made a mistake. It should be forward over reverse. Because, okay, hang on 1 second. Let me erase this over here. But the idea here is that we can use the chemical kinetics rate expression to determine the equilibrium expression. So rate forward over rate B equals, no, we know that KF over KR, we know that KF over KR equals rate F over A times rate backwards over the concentration of B and the concentration of C. And now if we multiply by the reciprocal, if we multiply this by the reciprocal, so rate F over A times B C over rate backwards. Since at equilibrium we know that the forward rate and the reverse rate are equal to each other, we get these cancel out, and then we get that Kf over Kr equals B C over A. And we collectively call Kf over Kr, Kc equals B C over A. So that's the full derivation. It's a pretty nice derivation. It's pretty nice to see that, okay, this isn't a coincidence, and this actually comes from something. But now that that's done, we get our equilibrium expression. And Le Chatelier's principle we discussed in the standard level syllabus. You're expected to know how to explain it in relation to kinetics, in relation to equilibrium expressions. It's pretty... I'm not going to go over that since you should know how Le Chatelier's principle works from the standard level video, and I actually go fairly in depth with this. However, what is new to the higher level syllabus is two things: thermodynamic considerations of equilibrium and the ice chart. Firstly, let's consider the thermodynamic considerations at equilibrium here, but first let me get a new sheet of paint, which I will need to do for the ice chart. The standard Gibbs free energy for change for a reaction, delta G, measures the difference in Gibbs free energy from the conversion of all reactants into the products. And what you're supposed to see here is that progress of reaction. So this is the Gibbs free energy on the y-axis, and the progress of the reaction is on the x-axis. And this dotted line is the change in Gibbs free energy. However, this is actually how the Gibbs free energy changes with respect to the progress of the reaction. And we can see here is that there's a minimum. There's a minimum amount of Gibbs free energy, and at this minimum, this is where equilibrium lies. This is where equilibrium lies, at this minimum of the Gibbs free energy. And for a spontaneous reaction, the Gibbs free energy will be negative, obviously, and this negative Gibbs free energy will correspond to high products, low reactants. A high amount of products, low amount of reactants, so a big Kc, while the inverse is true, whereas if the minimum was here, Kc would be very small and the Gibbs free energy would be positive. What you're meant to take away here is that delta G, or the slope, at this instant is 0, and if we draw a tangent line, it would make sense. Since that tangent line is flat, the change in Gibbs free energy is 0. The reason why this minimum Gibbs free energy corresponds here is that at this point there's a maximum amount of entropy. Since there's a little bit of reactant particles and a lot of product particles, that means the total number of particles is maximized, and therefore there's a high amount of positional entropy within this configuration. And then here, for a non-spontaneous reaction, we see that this the minimum lies less than halfway through the reaction, and therefore K is less than 1, and the Gibbs free energy change here is clearly positive. If delta G is 0, then the reaction is actually exactly halfway through, and there is no change in Gibbs free energy, and there's equal amount proportions of reactants and products, i.e. the equilibrium constant is 1. With respect to spontaneity of a reaction, K is an indicator of spontaneity, and the way we can do that is if K is bigger than 1, the change in Gibbs free energy is less than 0 and it's spontaneous, and the reason that is because there's mostly products in the mixture. And the inverse is true: if there's mostly reactants in the mixture, the reaction is not spontaneous and K is very small. And we can relate it to this formula here: delta G equals negative RT ln K. The only other thing the higher levels have to know how to do is solve for equilibrium positions given initial positions. Now, although we don't know the change, we can use something called an ice chart. An ice chart stands for initial, change, and equilibrium. Now, standard levels will probably not need to know how to do this as well. However, you're given the change. You're generally given the change, or it's very easy to figure out what the change is. However, so let's do this sample question here. And you'll get an idea of how to do one of these ice charts. I think that's the best way to do it. So say we had the following equilibrium: 2SO, 2 O2 plus 2 O. Whoops, I fucked it up. Plus O2 yields 2SO3. Now let's draw an ice chart here. ICE, so which stands for initial change in equilibrium, and we know that. And here, let's just separate this based on the SO2, O2, SO3. We are given that the initial concentrations are 0.700 molar and 0.500 molar, and you could assume that this initial concentration here is 0, since that's what it is. Now, firstly, I think a good you have to be given Kc in these questions, and we know that K equals 7.5 times 10 to the minus 2. You'll be given K in these questions, and generally a good habit is first to calculate Q and determine what way the reaction is going to shift. Now, we know that for the sake of doing it, let's calculate it. So since there's no product, obviously the only way for it to shift is towards the product side. So therefore, and although we don't know the change, let's say plus x. Now we can relate these stoichiometrically. This would be plus x, and this would be minus a half x. Now, just to make our lives easier, since x is just some unknown that we're going to solve for, why don't we work with nicer numbers here? And oh, did I put a plus there? I just realized that should be minus. Let's make our lives a little bit easier. Let's call this minus 2x, let's call this plus 2x, and let's call this minus x, just so that we don't have to work with fractions. So then we know the equilibrium is 0.700 minus 2x, 0.500 subtract x, and then 2x. Now we can plug this into our equilibrium expression, which we know that Kc equals SO3 squared over SO2 squared, and then O2. And then plugging our numbers in, we get that 7.5 times, should be a 5, 10, oh, fuck me, 10 to the minus 2 equals 2x squared, 0.700 subtract 2x, and then we get that 0.500 subtract x, and then all you need to do is you can just plug this into a calculator, and you get that x is equal to x equals GDC. By graphic display calculator, or GDC, we get that x is equal to 0.054. And that's the answer. And then once you know what x is, you can just plug in your numbers back here and get all the equilibrium concentrations, which is generally what you want. You can use Solver on a TI calculator, but since this isn't a math class, I'm not going to teach you how Solver works. You're going to have to work that out yourself. Or you can plug it into PolySmelt and it'll solve it. But generally, that's how you go about these problems. So with that, thank you very much for watching.